But anyway, Max, real quick, introduce your talk, differentiable programming in D. It's a pretty heavy duty topic.
Yes, the idea is that unless anyone's been living under a rock, obviously like sort of AI and so on is like the fad at the moment. We've had some kind of limited forays into that space with D libraries, and the modern kind of collection of techniques for doing that are basically known as differentiable programming. I like the way of actually specifying the models and then training them. So I'm kind of giving an introduction to sort of the two kind of basic techniques, doing something very simple. And then I think I've mentioned how that connects to things you can see kind of in the more kind of quote unquote industrial libraries. And then what you'll see in the talk will eventually turn into a proper library at some point. I spend the first bit introducing a technique which is more useful for differentiating kind of old school models, if you just want to fit a curve versus fitting like a billion parameter neural network. One is slightly more practically useful to D programmers, and also is something that we do in a nameless code base inside Symmetry.
With your major, I guess calculus was an important, a critical component of that. I don't think you covered this in the talk, but what are some use cases, some practical use cases for a library for the D community?
If we kind of skip anything kind of like vaguely scientific, I was actually going out looking for kind of interesting ways to use this. And like what the thing I was kind of using as a benchmark is, would a game use this? If I come up with my tail between my legs, I haven't actually got anything like particularly cool. But there are some things where if you imagine having this available, if you want to be able to like fit Bezier curves or something, or you want to be able to do like draw like a smooth, like fit a smooth path for something in a game for like a particle to follow. I think that'd be very useful to have this kind of thing without having to either roll it yourself or use some kind of approximate method that doesn't work. It's very useful when you need it, but without necessarily the right background, you wouldn't even know you need it. There are always uses, like there are some quite applied mathematics, but I know that you can use some of the techniques in this in the form of like hacking around with PyTorch. You can have like a game of life. There's someone who's built a thing where you can actually invert a game of life almost, so you can actually like make it generate an image that you want based on the starting conditions, but that's still kind of just sort of mathematical trickery. If I think of something, I'll say, mainly because I won't be able to stop myself saying it. But
well, Walter has something here in the live stream chat. He says, I confess I'm not sure why I wouldn't just do the symbolic differentiation myself.
Well, I mean, you can. It depends on the model, because like something I work on inside Symmetry does do that, where it has the model is designed in a way where it basically uses some tricks. Well, like if you want the differential with respect to the xth parameter, you can actually just multiply it by a factor. So it's actually designed in a way to be easily differentiable. But the reason to do it is basically it doesn't scale, and also there are actually some things you can do where if you want to be able to scale it to different hardware, so you want to be able to run it on GPUs, then you basically have to use these techniques. Otherwise, it just isn't going to work. Basically, like you can do like the Vectorflow library that Netflix did for the neural networks. That basically is the equivalent of doing symbolic differentiation on paper and then writing it down as D code and then running it like that. But that means that it can basically only do what it's been coded to do. Whereas if you use a library that uses these techniques, then changing the code is just changing the model versus maintaining a separate kind of symbolic specification of what the model does and then differentiating that. But there's a tiny hint of that at the end of the talk, assuming I mentioned it, because I mentioned Mathematica at the end. Mathematica can output C code, which obviously we can compile. You can compile code which has been outputted from like Mathematica or MATLAB or whatever, but I've done that and it's just horrible. And there are also things as well where the symbolic techniques can't actually support things like loops, for example. So if you just want to write code and you need to hack something together, like you end up needing a loop because you can't quite write something this way, that way, the other, you actually can support that with a lot of automatic differentiation routines, whereas you can't with a symbolic thing unless you're extremely clever or very lucky. There is a project called Enzyme where you can actually differentiate through a computational fluid dynamics solver. So you can actually get like derivatives out of the end of it, which is pretty much impossible with a kind of like classical CFD implementation. That being said, I can't find that demo. I'll have to link it somewhere. And yeah, there's something that Nicholas Wilson and I have been looking at kind of working with LDC. There's a slight hesitancy in that would mean locking it into people using LDC, which is a bit of a shame.
I have another question from Walter here that we'll give instead of my trivial one. Are you doing this in the front end or in the intermediate code?
If that's referring to Enzyme, then it works on LVMIR. One of the reasons why they get like very good benchmarking numbers is that they're being quite clever and doing it in between some of the optimizations, if I recall correctly, which is a shame because you can do this on the front end, especially for the reverse mode stuff where you have to build a graph. The compiler already has a graph. You just have to serialize it into something that you can actually interpret. It's just someone has to write the code and test it, whereas Enzyme's already been written.
So my question was, I was looking at that slide about your how fast you were traveling, and I was curious where you compiled that data from.
It's from an app on my phone. There's an app called Fizzbox where you can press record, and then it will use the GPS to record the kind of data. It's using the accelerometer and the GPS. So it is real data. That is actually me in a train from where was it? Bath or somewhere. Our glorious class 802 trains that can do quote unquote high speed of almost 80 miles an hour on some bits of the track.
This is like so far out of my realm of knowledge. I'm just going to have to ask you to fill in some gaps here. What are some things you didn't say in the presentation that you think would be interesting for people to know when they're watching this Q&A video later?
Well, one thing I was going to talk about is that there have been a few people who've attempted to implement libraries to do this, kind of industrial ones on the GPU. And I've only played with one of them, but I think they've mostly had taken, I think some of them people have just hadn't had enough time to finish, but there have been a few where people have had enough time, but they've also, the things they've implemented have been kind of slightly unfortunate in terms of the design decisions they've made without kind of like blaming anyone, but kind of like there's just ever so slightly things where like they're quite hard to extend. Like Vectorflow is the one that Netflix did, which is actually quite readable. Then there's Grain, which is done by a Japanese person, but I think and Grain 2, which I think probably works when you have more of a play with it. But I think I had a play with Grain 2, but the difference between the two of them is the word autograd in the summary of Grain, where basically you maintain that kind of dynamic graph of operations and then work on that at runtime and then do everything through that rather than what Vectorflow does, which is much more closer to what I said when I was responding to Walter, where it's basically a structure that you've worked out beforehand and then you've actually sort of written down all the equations just as code. It's not quite that simple, but like it's a much less dynamic and expressive way of doing things, but it's also more direct.
Well, let me ask you this. What would you suggest to somebody who doesn't have the background for this or who doesn't remember the background for this? Where would you suggest them to go to
play with PyTorch?
You don't see any need for prerequisite knowledge, a prerequisite study?
Well, I mean, it depends because, like, on the one hand, I think there are way too many people in the kind of AI stroke data science industry who don't actually know anything about what they're doing, if I'm being blunt. But, like, one of the things that's interesting about this is if you imagine, like, kind of old school AI where you have sort of like tic-tac-toe and that kind of like sort of solving games by like looking through trees of moves. And the thing that's interesting about the more modern kind of neural network flavored AI is that you can, up to a point, basically just throw training data and computing at the problem and then kind of just play around with the structure of the network until you get the result that you want. It's a much more kind of tractable way of going about things. Like you do need a certain intuition about numbers, but like if you actually just want to do AI work, you don't really need to sit down and solve any equations or anything like that. This is basically just a more of like a teaching it from the bottom up rather than the top down, because I've met people who even kind of work in the field who I'm not sure actually understand kind of the roots of how the things that they're using actually work. Partly because it doesn't actually matter in a sense, in that like it doesn't actually stop you from doing any work if you want to be an AI researcher. But there's also an element of like John Carmack's working on AI now. He's actually just left Meta. So he's founded a company called Keen Technologies to work on AI. And I think one of the things that he's trying to do is that even if they can't, like it's unlikely that they're gonna invent HAL 9000 like intelligence that can actually compete with a human. But one thing they can do is that he's obviously like old school programmer who actually, you know, he's a fan of like static analysis and good code. And I think they could really kind of shake up the industry a bit if they kind of instill that kind of old school wisdom upon the Python monkeys. The
question from Francesco is, could you recommend me a book?
Yes. There's one called the Elements of Statistical Learning, which is quite a good one. But it depends on what the background is that you want to start with. But this is a good one. Also, I'll stick it in the chat there. You may or may not be able to get that for free on Google if you just search for that appended with PDF. But it depends. If you just want to like do some work versus learn like the fundamentals of machine learning in the kind of mathematical sense, then that depends. But there's one that I learned that what used to be the link to the book now seems to be a link to a GitHub thing for some reason. But there you go. That's a machine learning, a probabilistic perspective. It's a classic, although that one does have the disadvantage of it's one of these books where like there's the kind of the cool stuff that everyone's doing in industry, but that's on page 600. But there's a bit of a slog.
And my question from Ricky for you, Max, is are there any plans for a nice, easy to use ML library?
Well, there's always plans. That's basically the dream. I think the thing is to get a simple foundation layer that can basically do the things I've mentioned in this talk, but on tensors, get that working, and then, which for the record might already exist, because that could just be grain. But I think to get that working simply, and I suspect in a way that actually isn't a particularly idiomatic deprogramming, and I think there have been things where people have tried to do too much D stuff that doesn't matter, because if you imagine a lot of the tricks that you can do in D come from trying to make things work faster on CPUs, but you actually want to make it run on a GPU, and then you can kind of control everything based on the stuff you've collected when you were building the graph. On top of that, like building the ML stuff on top of that is actually relatively easy. You can train the neural network with either of the things I've mentioned in my talk. And then when you get a larger one, that's when you have to go on the GPU. It does get complicated after that, in that there are things you have to do in terms of the operations you choose to support and how you express things that will affect how you go about doing things. But just to get something working, like not caring about performance, is actually not that hard of actually writing the code and getting it right. So I've just posted a bunch of links onto the news group.
In the announce forum or the general forum?
General.
Okay.
I've also stuck one on the end, which is something called tinygrad, which is a project by George Hotz, which is basically a very kind of cut down kind of machine learning framework, which is something that I think we could probably emulate relatively easily, because the tinygrad aspects comes from the kind of the core of PyTorch, which actually does the maths, is called autograd, and currently downloading that on a laptop is like between 1 and 2 gigabytes with the amount of like stuff it carts around, because it basically carts around everything it could possibly need to support every graphics card under the sun. So it will quite happily download the Python package. You're just waiting for it to install for like a billion years. The idea was to make a very cut down one, which is not just aiming to be simple, but also aiming to be aggressively simple in some quite clever ways to make it easy to accelerate, to write neural network accelerators for, i.e. custom hardware, which they haven't done but could well do. Fabrice Bellard has done some work with this too. He wrote LibNC, which is basically a machine learning framework, which he actually wrote in C, which is unfortunately closed source, but has some kind of interesting tricks there. You can download and have a play with it. It's actually quite easy to use, considering it's written in C, because it comes with a header file. You can actually see all the data structures inside of it. Not that it's a particularly complicated thing, but like you can see how the tensors, like the n-dimensional arrays, are laid out and how it represents the strides and things like that, which is kind of fun. And it also works on the GPU as well. So it actually, he can do all that in just under a megabyte, whereas PyTorch is about like a gigabyte or something of Python and compiled C++.
Yeah, we've got a question from Brian Callahan here. I know Enzyme only works with LLVMIR, so it's only usable with LDC. Is there a minimum version of LDC you need, or will any do?
Well, there's a minimum. There are multiple minimums and maximums, because there are some things with LVM, which you're probably aware of, which are changing around at the moment. Like there's the new LVM pass manager, and there's the untyped opaque pointers, which I would imagine the Enzyme people are on top of now, but I'm not sure because I was in a meeting with them maybe too many weeks ago now, where we were having a chat about this, and I think at the time they weren't quite ready to get the two talking to each other. But what you can do is you can try it, because it's actually just an LVM plugin, so you can actually load it either at compile time or at link time if you use LTO, and have a play with it. I think as long as it has C linkage, I'll get confused with any APIs. It should just work. I've attempted to post a link. If not, it's on the Enzyme website on Getting Started. They have this absolutely crazy way of annotating what you want to differentiate with respect to, because they've had to basically hack it around basically C. So what Nicholas Wilson and I were talking about doing is using their internal libraries to make it so you can just annotate things with user-defined attributes, and then LDC just manages it all for you. But that then would lock you into an LDC version. But this hasn't been done yet. Using it as a plugin should just work, though. That's basically the takeaway. I say not having tried it on anything quote unquote serious. Oh, you can also try it on the internet as well. They have their own compiler explorer thing with their like enzymified Clang that you can play with, which I highly recommend playing with. But partly you can also see what it's doing with in the assembly. Enzyme is more aimed at kind of traditional scientific computing as opposed to machine learning as per se.
If you were not working for Symmetry and working on the pull requests and stuff you do for the D community, where would you spend your time? Would you spend your time on a project like this? On a project using?
Maybe.
Yeah.
Maybe. It depends. Like, it's almost disgusting the amount of money like you can get as an AI startup these days. So there's an element of kind of following the money. Solving problems with it is kind of mainly what I'm interested in. I don't find it particularly intellectually satisfying. There's a very famous debate between Chomsky and Peter Norvig about basically statistical approaches to linguistics. There's kind of an element of that where you're kind of like, it's very effective, but I don't find it particularly intellectually satisfying to do. There's a very beautiful structure on the inside, but what I see it as more of a way to solve problems as opposed to like a kind of a be all and end all, like,
Max, why don't you go ahead and close us out with some parting thoughts?
Keep your eyes peeled for more. If I successfully organize myself enough to actually write the library I'm talking about, eyes peeled, more blog posts about this. And also I'd like to finish also by saying that the thing that Feng was going to present, I have actually looked at the code for that. When that does go out, everyone be excited for it, because it is actually quite interesting. And they have, I think Google have used it for something for UVM testing or some RISC-V stuff.
Yeah, I was really hoping to have that talk on the schedule because one, we've never had a presentation from any members of our Chinese user base at any of our conferences, and two, it's a really interesting project. And I enjoyed the presentation that he sent me, but unfortunately it was unusable for reasons. But he's promised to get me the new version of the video as soon as he can, and I'm going to upload it to the YouTube channel after the conference. So we will be able to see it eventually. All right, Max, thanks for joining us today. Thanks for submitting the talk, and thanks for coming back in at the last minute. And I wasn't sure how the schedule was going to pan out today. I was hoping Feng would be here, but thanks for joining us. And I want to say that we picked